Good day, matey. 1.4, day number 2, trig functions and their inverses. Objectives, periodic functions, transformation of sine, cosine, tangent, and a little bit of inverse trig. So let me throw something up there that you've seen before. And let's talk through some of those old details. Let's go theta minus c plus d. Let's identify this. If I take the absolute value of the value a, I get what's called the amplitude. This should be stuff that's coming back. The absolute value of, b is going to be related to the period. Right? So 2 pi, as long as this is sine or cosine here, 2 pi divided by the absolute value of b will give us the period. C is our horizontal shift. Has been and probably always will be called the phase shift. And the value for D is our vertical shift. If D is positive, it's shifted up, negative, shifted down. If C is negative, right, minus C, then we get a shift to the right, positive, we get a shift to the left. B has to do with horizontal stretch or compression, and A has to do with a vertical stretch or compression. So period for sine and cosine is 2 pi. The period for tangent is just pi. So that equation right there applies only to sine and cosine. The only difference between the two would be if this were tangent, that would just be pi instead of 2 pi. So it's all good. Let's move on. So yeah, let's graph sine of 2 theta. There's no vertical stretch, there's no vertical shift, there's no horizontal shift, there's just a horizontal compression. It's not been stretched horizontally, it's been compressed. It's the opposite of what you think on the inside. Therefore, 2 pi divided by b is our new period, and b is 2. So our new period is pi instead of 2 pi. So instead of the sine function stretching out to 2 pi, it's only going to stretch out to pi. Okay, so we just accommodate that by changing our values here. So again, no vertical stretch, so this should be a 1 and a negative 1, and there is 1 period of sine of 2x. Okay, what about 2 cosine x? So horizontally, nothing's going on. Vertically, we're stretching this function. We're not shifting it at all. So we're going to draw our normal cosine function and then just relabel. So here is a full period from 0 to 2 pi. Right? It's going to go through those values. We sketch, hopefully symmetrically, and good enough. Now it's been stretched by a factor of 2, so it's now been stretched from negative 1 to 1, now to 2 to negative 2. All right, let's graph y equals sine x and y equals inverse sine x on the interval negative pi over 2 to pi over 2. So I'm going to do a little bit off camera here, and I'll come back and talk you through some of it. Okay, so here I've got this interval from negative pi over 2 to pi over 2. I'm going to graph sine x first. And sine x will hit its maximum value here at pi over 2, which is 1. And its min value down here at negative pi over 2 at negative 1. So sine of negative pi over 2 is negative 1, as we know. Sine of pi over 2 is 1. Okay, so now we're going to graph the inverse sine of x on that same set of axes. But first, I do want to talk about domain. So what is the domain of sine x in this case? Well, we had artificially restricted it to negative pi over 2 to pi over 2. And its range, as we know, we go from negative 1 to positive 1. All right, so what's going to happen with our inverse? Our inverse is going to acquire the domain as its range, and the range is its domain. So the range of sine x will now become the domain of inverse sine x. And the domain of sine x will become the range of inverse sine x. So now our domain all right, is going to become the range and the opposite. So let's give this a nice sketch. Okay, so this graph isn't perfectly square. Negative pi over 2 is like negative 1.6. Okay, so the graph, you might not be satisfied with this, but basically what's going to happen is we're going to get a function that looks something like that, and it's not a great sketch. Okay, it's not perfect, but what we get is this reflection over the line y equals x. Okay, let's use purple for that. There's your line y equals x, and we get this thing called inverse sine of x. All right, let's move on. Let's do the inverse tangent of x, and let's go on the interval from negative pi over 2 to pi over 2. So tangent, the domain, like we said, we've restricted. And its range actually is going to be all real numbers. So y is, well, that would be, let's just say all real numbers. That works for me. So we'll do that for the tangent. Let's go ahead and graph that. Let's go negative pi over 2 out to pi over 2. And our graph, of course, asymptotes. Our graph will look like this. Okay, you can see the range is not limited, but the domain, we have these imaginary, phone booth walls that are restricting that. Okay, so the inverse tangent is going to take on the flipped restrictions. So now the domain is all real numbers, and the range is negative pi over 2 to pi over 2. So what does that look like? We had vertical asymptotes at pi over 2 and negative pi over 2. Now we're going to have horizontal asymptotes at pi over 2 and negative pi over 2. So we got these horizontal asymptotes. We're going to have some symmetry here. It's going to be kind of funky, but here we go. Let's try it. There it is. Okay, there's inverse tangent. You'll notice the limits as the inverse tangent approaches infinity going to the right. It's going to approach pi over 2. So again, let's draw y equals x. It's not going to look perfect, but because of the skewed orientation of this, but those would be symmetrical. All right, last one, inverse cosine. I'm actually going to do this off camera and talk about it in just a second. All right, so cosine has a domain restricted from 0 to pi, which means its output values or range would be negative 1 to 1. Okay, so in green you see cosine. And then in red, I've got the domain, the new domain of, oh gosh, really? The new domain of the inverse cosine and its graph. And of course, I did a better job of drawing this symmetrically. Okay, you get here the line y equals x, and there's your graph. All right, so let's talk about inverse trig. Inverse trig is an angle. So your answer to any question that looks like this is going to be an angle measure. So this is basically asking you, what angle has a sine of 1/2? Now, a couple things you got to be privy to. If you're talking inverse sine or you're talking inverse tangent, your answers have to be between negative pi over 2 and pi over 2. Oops, that should be close bracket. Okay, if we're talking inverse cosine, then our answers would have to be between 0 and pi, which are the restrictions we put on those earlier. So just to be aware of. Okay, so inverse sine of 1/2, that means I want a sine value that's positive. So that means it's got to be in quadrant 1 up here, right? And it's got a sine of 1/2. So sine of 1/2, that to me is just screaming pi over 6. Okay, inverse cosine of 1 over root 2. Okay, anytime I see a 1 over root 2, I think some kind of pi over 4. Cosine is positive. in quadrant 1 as well. Therefore, that's got to be pi over 4. And inverse tangent equal to 1. Anytime you see inverse tangent equal to 1 or negative 1, you should also think pi over 4. Since tangent is positive, it'll be positive in quadrant 1. It won't be in quadrant 4. Therefore, that answer would also have to be pi over 4. Let's keep going. The tangent now is negative. If we're talking inverse tangent, that means our answer is going to be in quadrant 4. Okay, so that means we're going to have a negative angle. Okay, so let's think about that. Let's go here. I got a tangent. And this isn't drawn well, but looks like tangent is negative 1 over root 3. That to me is just screaming negative pi over 6. Even though I didn't draw that to scale, I should probably redraw it. How about this? That's positive root 3, negative 1, and that's a 2. That right there has to be negative pi over 6. Now, cosecant. That's a mess. All that I would do is I would change this into the sine inverse and flip this inside, right? Because they're reciprocals. It won't change anything. So this is really asking also, where is the sine? At what angle is the sine negative 1? And we would say at negative pi over 2. Right? That's the only place in either quadrant 1 or 4 where that would be true. Okay, something a little bit more abstract. What if theta equaled inverse sine of 2 over 5? Find cosine and tangent. Well, what I would do, since it's positive and this is inverse sine, I'd place this in quadrant 1. If sine is 2 over 5, then I'd use Pythagorean theorem to get root 21 there. This is theta, right? How did I get root 21? I took Pythagorean theorem, I worked it out, right? So 2 squared plus, let's call it x squared equals 5 squared. Well, x squared would then have to equal 21, which means x has to equal root 21. So now I can come up with the cosine. The cosine would be adjacent over hypotenuse, which would be root 21 over 5. And the tangent of theta would be 2 over root 21. All right. When in doubt on problems like this, draw a triangle. Just draw a triangle, and it'll get you to where you need to go. So here, there's no numbers involved. How the heck am I supposed to do this without a calculator? Well, I would treat the inside of this as theta. Right, I'm just going to draw an angle that has, in this case, what was it? Tangent. So I'm going to say tangent inverse, tangent of x equals theta. Well, I'm going to assume x is positive for the moment. So the tangent is x. That means it's got to be x over 1. Opposite over adjacent is x over 1. Therefore, the hypotenuse, generally speaking, would be 1 plus square root of 1 plus x squared. So what would the sine of theta be? Right, because all that inverse tangent x is theta. It's a representation of an angle. So the sine of that would have to be x over the square root of 1 plus x squared. And folks, that's it. That's our last lesson for chapter 1. That's section 1.4, day number 2. We'll move on to limits in the next few days. So, yep, have a good one. Don't forget to do your push-ups.